Thank you very much, Andrew. Hello, everyone. So I'm going to be talking about, as Andrew said, decentralized kernel CI. What that means, what's been going on in the community overall, and what I've been doing. So my name is Russell. I work at IBM at Oz Labs in Canberra. You're probably sick of hearing people from there so far today. I was working on the PCI stack for a while, but now I've decided I want to be cool, so I'm working on hardening. So today I'm going to be talking about kernel CI, what's going on. I'm going to be talking about my project, snowpatch, and how it's hopefully going to change the world in that space. So what exactly is CI? And a lot of people use the term and maybe don't know exactly what it meant. So this is a quote from Microsoft, and it says that CI is the process of automating the build and testing of code every time a team member commits changes to version control. So it's from very much the agile world of development that we all loathe, probably. But I think the key thing that a lot of people miss when they talk about CI is feedback, and there's a quote here that I quite like, that CI at its core is about feedback, and it's about implementing a process that facilitates feedback so that problems can be identified and corrected early in the development process when it's easy to diagnose and correct them. So the sooner that a developer knows that something they did has a problem, the sooner that they fix it, the better the world is. So when you send a patch to a mailing list, let's say it has some obvious bug in it, and this is an obvious bug. You know, maybe you'll get a reply in a day or two from a reviewer or a maintainer who looks at it and tells you. Maybe no one even looks at your patch, maybe no one cares. But if you found out about that straight away, maybe 10 minutes, half an hour after you sent it, then you'd have a V2 on the list straight away and save everyone a bunch of time. There's another big factor here, which is CI can obviously run tests to catch things that humans aren't so good at doing, whether that's something really obscure or whether it's just, it takes a lot of time to find out whether a patch does something or doesn't. So the whole code submission process gets faster. The faster you can fix something without humans' help, the faster that your code gets in, the less time reviewers and maintainers have to spend. So what would this look like in a kernel context? Well, you send a patch, then some automated system merges the patch to whatever branch it's supposed to go to. You would run tests on it. It could be something simple starting out, just like check patch, which everyone always runs before they send their patches, of course. And then building up to doing a build matrix, various configs and platforms and architectures, and then getting into some heavier tests if you have the infrastructure, like actually booting the thing. You could do self-tests, you could do all sorts of stuff in user space, depending on what you wanted to do. And then the most important thing is at the end, reporting the results back to the developer. So what exactly makes this hard? Projects do this type of thing all the time. You know, if you look at GitHub, any decently sized project on GitHub is going to have all sorts of test automation going on, but it's a lot easier to work with things like GitHub and GitLab than it is with a patch on a mailing list. So this is kind of why. This is a patch that was sent to a mailing list. This is the this is the start of a patch from Christophe Leroy to the Linux PPC dev and LKML mailing list. And you can see a bunch of stuff about the body of code inside here. You can see that this is revision 13 of this particular series. Of course, you don't know where the rest of the series is. You just have an email. You can see this is patch 7 of 10. And that's pretty cool, but where's the other 9? Do we know that all of them have even made it to the mailing list yet? This is a bunch of stuff that takes a lot of fiddling to do, whereas if you look at this, wow, look, all 15 commits are there. It's already in a branch that you can go ahead and test. When you have a patch, you don't know that it was applied to the maintainer's next branch, or Linux next, or mainline from a month ago. That's a bunch of information you don't know, which obviously you need to know if you want to actually go test the thing. So it's a lot more difficult to get the metadata you need to actually do continuous integration when you're dealing with a mailing list. And that's the fundamental problem here that makes this difficult. Mailing lists have a huge lack of metadata, and it's hard to know not only stuff about the body of code itself, but also where it sits in terms of the development cycle. Has the maintainer merged it? In which case, we probably don't need to go test it. If it's been rejected, we don't need to go test it. If there's a new revision of that series, we don't need to go test it. So all of that stuff is difficult. So before I get into how we solve all these difficult problems, let's talk about who's already doing kernel CI in the community. So we have the biggest one, of course, is Intel's zero-day service. I'll mention kernel.ci.org. That's not doing the type of patch-by-patch testing CI that I'm talking about today. They're looking at having a gazillion boards in a big test farm and then building stuff on them all the time. But if you tried to build every single patch on every mailing list on every piece of hardware imaginable, the world would explode. So that's not quite what I'm talking about today. There's snowpatch, which we're mostly running on Linux PPC Dev, which is what I'm talking about. And I'm sure there's plenty of maintainers that have some amount of automation for what's going on in their lists, because there's too much work to do otherwise. And there's probably some other stuff that I'm not aware of, so please do tell me about those. So let's talk about 0 day, which is kind of the big boy in the world, I suppose. According to their website, it tests against more than 100 different kernel configs, does all sorts of clever things, right? Especially on x86, it does some static analysis, it runs a bunch of performance tests and will kind of flag if something makes something drastically slower. It will send you an email report on failure, so I'm sure you've all seen 0 day bot tell you that you broke 32-bit, because that happens quite a lot. And 0 day is a really impressive project. The downside is that it's proprietary, it's run by a team at Intel, so you can't take it and go ahead and do whatever the heck you want. Similarly, a lot of the fancy stuff they only do for the architecture that they care about. So 0 day is awesome, but you can't get it to do what you want. And the other thing is that when you only send a report on failure, you don't have any kind of receipt saying that, yes, we have actually tested this patch and it builds. If you're a maintainer and you're not on an x86 list or something, you can't actually know for sure that this patch you're thinking about merging has passed all the smoke tests that the bot has run. You don't have that receipt. You only get a receipt if it's broken, but you can't confirm that it's not broken. So how exactly do we bridge the gap with, kids these days in their GitHub and GitLab? Well, it's a problem too, because if this was a lot of other projects, we could say, okay, cool, we'll just run a GitLab instance or put it on GitHub and do it that way. But everyone knows that that's not going to happen. We can't just uplift the entire development of the kernel that works so well. I mean, we've got very large, very distributed, decentralized project here that you can't just apply traditional methodologies to. So how exactly do we do this? And as you can tell by me being up here, I have opinions on this. So my suggested solution comes in the form of using Patchwork as our source of state. And Patchwork, if you haven't seen it before, it's a web-based patch tracking system. I'll show you more about it in a second, but this is what it looks like. It's designed to supplement mailing lists and not replace them. So it's a web-based view. It gives you an idea of what's going on in the mailing list. It will sort things into series. It will let you know if a patch has been merged or superseded or what have you. It's already used by the kernel, so this is any crazy new infrastructure. I think probably the majority of mailing lists are already on Patchwork, whether it's on kernel.org or it's on ozlabs.org, which are the two biggest Patchwork instances. You can go to patchwork.those things and find them. And the important thing about Patchwork is that you can push test results to it. So when you have a list of a mailing list on Patchwork, you can see, the series that are on there, their kind of state. Maybe they've already been merged, maybe they're under review, whatever. And you can go and see, will do these things pass any kind of tests? And the important thing for us in terms of people trying to build this continuous integration infrastructure is that it has a JSON API. So you can do magic with it, whether you're someone like me who just wants to automate a whole bunch of everything, or if you're a maintainer who wants to add some magic to your merging process, whatever. So quick look at Patchwork itself. This is a patch list of the Linux PPC Dev mailing list. On the left you have every patch. On the middle you've got the series they're in, so you can easily find what's actually in the series. It tracks, in this case, I think that's axe fixes, reviewed bys and tested bys, I think. And the important column here is the SWF one, if you can see that. That is successes, warnings, and failures. So those are test results. So if you send a patch, you really want the S's to be more than the F's, I suppose. On the right, you can see a bunch of patch state. Now, one important thing to know about Patchwork is that patch state on the right, in terms of things that have been accepted or rejected or what have you, you're only going to get that information if your maintainer actually uses Patchwork. So that's important to note. So if we go into what a patch looks like itself, well, this is what you get. You can see the patch itself. You can see that it's accepted. So this is a patch to do some DMA stuff from Christoph Helbig. And you can see that it's got all these checks listed here. So These are test results that have been sent to Patchwork for this patch automatically by snowpatch. I'll get into that a bit later, but you can see here that we're doing a bunch of different tests. First of all, we're just doing check patch, and then we're doing 4 different builds in our particular case of what we're running. Now, the cool thing about these builds is that basically what we're doing is we are building the base branch with spars, then we are applying this patch on top of it, we're running spars again, and then doing a smart diff of the spars results to see if we get any new warnings, or any less warnings, because less warnings is probably pretty good. So that's kind of that's what you see when you go to any patch that's on the list that's running these kind of tests. So why exactly would we use Patchwork? Well, we could, send via email every single test that we run on every single patch, but I don't think anyone wants their email blown up like that. It's a bit too much. We don't want to be invasive. If people just refuse to look at what we run, that's their business, I suppose. Patchwork is already used in the kernel. Different maintainers, some don't use it at all, some use it a lot, but it's already in the ecosystem, I suppose. It's already out there. People are already used to it. It doesn't change the workflow of developers. There's nothing changes about how you submit code or how you get reviewed feedback or any of that core thing about software development. It's still centered on the mailing list. This is just sort of a cleaner view of it. And I think the key thing in terms of a continuous integration approach that can actually work in something as decentralized as the kernel is that test results can come from absolutely anywhere. You have a whole bunch of different individuals and companies submitting code to the kernel. They can all be running their own tests internally on their own hardware on the things that they individually care about, and then they can send those results publicly where everyone can see. So in my dream fantasy world, which you don't want to know about everything in there, but one thing in there is that you have multiple companies working on stuff on a mailing list, and the developer sends a patch and can see that it works on these 2 people's hardware and it broke this guy's hardware. So that kind of decentralized testing where none of those test environments can see each other, right? They're all internal to a company, but the results from them can all be public. So how exactly do we do this? How do we put all this magic together to make a continuous integration workflow that we run all the time on every single patch that someone sends to a mailing list? Well, we get the patch and its dependencies from the Patchwork API. So let's say we're testing, patch 7 out of 10. Then, we need to find patches 1 through 6 and apply them in order first. And then we apply number 7. And we go off, make that a branch and go test that. So we apply it to every branch that we care about. It's a bit difficult in kernel land because you don't know exactly what something was based off of, typically. So we apply it on something that we care about. We push that branch to a remote so that we have some testing thing that can go off and grab it and run with it, trigger the tests, wait for them to finish, and then push the results to Patchwork. So that's the basic workflow. And the thing that I wrote alongside our gracious mini-conf host, Andrew, is snowpatch. So snowpatch is a Rust program because, again, I'm really trying to be cool. So to kind of automate this flow, and it's essentially based around using the Patchwork API as its source of information to go off and do this process. I actually started writing it at LCA Geelong because I don't know why, that's just what I did. It's running in production now, and by in production I mean we're publicly pushing results, running on every single patch that hits Linux PPC dev. It's also running on a couple other lists. And it's still early days, very much in development, but it does work mostly. And it's GPL as well, so you can grab it and do whatever the GPL lets you. So in terms of, aside from Patchwork, the infrastructure that we use to do this, obviously we need some kind of engine that can actually execute tests. And right now I'm kind of sorry to say that right now we just support Jenkins. Yeah, I know. Jenkins has an API that we can start tests with. It does everything we need it to do, but obviously we definitely want to support more than this, even if it's just something like a simple, command line runner that we can get results from return codes or whatever. So patch is welcome because we definitely don't want to just support Jenkins, but right now that's what we're rolling with. So let's look at an example job, and this is the spars diffing workflow that I talked about before, where we have a sort of a base branch that we build and do spars on. Then we apply the patch on top of it, run that again, and compare the spars output to see if there's any new or removed warnings. So we pass those 2 references in, we pass where the repo is, and a def config. In this case, we change def configs all the time to switch between 32-bit and 64-bit and embedded and that kind of stuff for power. So this is kind of the API call we're making, and in theory, hopefully, we can do this with things that aren't Jenkins. That's the dream. So what do you need to get all this going? Well, obviously you need a local repository because that's how we apply things. You need, if you want to push results publicly, then you're going to need Patchwork credentials, and you need the project's maintainers' permission to do this. So you couldn't just pollute mailing lists with a billion worthless tests. You do actually need permission from the maintainer before you can do this on Patchwork. You need a Jenkins server in this case to actually execute your tests, and then you need to be able to push your branch to somewhere that Jenkins can grab it. So you kind of throw all this together, you tell snowpatch about it with this config file. So this is where Patchwork is, where Jenkins is. This is a project, so it's Linux PPC dev. We're saying that we're going to try to apply stuff to branches master indexed. We're telling it where we're going to push things so that Jenkins can see it. And then we tell it about a job we're going to run. So in this case, we're calling it build PPC64LE. That's the name of the job in Jenkins to go call. We tell it what parameters to populate with the branch that it magically creates. In this case, for our sparse build, we're telling snowpatch that it's hefty, which is a great word, which essentially just indicates that we don't want to run this on patches 1 through 14 of a 15 patch series. We only want to run it on the complete series because it's too computationally heavy. And we're setting some other parameters. And so then you run the thing and it will just do this for every single patch on your mailing list. Every single patch that you have on your mailing list, you just go in there and you'll have all these results. In this case, what's this one? We have a patch from Arndt that introduced a sparse warning on all PPC64 platforms. And so from there, obviously it's Patchwork. Below this, you have a view of the commit message in the patch and all replies to the patch. But if you go into any of these, you'll get more detail. In this case, we click on the new sparse warning, we can see that something should have been static. And so this is just a simple example of something you can do with it, this sparse diffing. You could do whatever the heck it is you want. Obviously, quite often we find things like build failures, most commonly people forgetting that 32-bit exists, but there's a lot more you can do with this. The more you build out your testing infrastructure, and maybe you already have some testing infrastructure that you could kind of put in here, as you build out that capability, you can do a lot of stuff here, and you can do a lot of cool things that humans are never going to test for, or that humans aren't particularly good at seeing, or that humans just don't really want to do. So why exactly do I think that this kind of overview, using Patchwork as the source of knowledge, is the way to go? Well, as I said before, it's existing infrastructure. It's nothing new and crazy. The results can come from anywhere. So they can come from multiple different companies working on the same thing without those needing to interact individually. So long as the maintainer okays it. Again, you can do whatever it is you actually want to do, whatever amount of testing or what have you. Snowpatch will let you do it. And it complements mailing lists. We're not upending any part of the kernel development process. We are just supplementing it. We're not doing anything radical or crazy here. We're keeping the existing development methodology of the kernel. So what else can you do with this, aside from some of the stuff I've been doing? Well, you don't actually have to make your results public. If you're making some super cool piece of hardware and you want to see how much butt it kicks and see if anyone who's contributing upstream somehow makes it slower, well, you can do that. You can either use a public Patchwork as your knowledge source for a mailing list and just not report the results upstream. You could run your own internal Patchwork and have a really nice view of every patch in the test results without your competitors knowing about it. You can do some crazy stuff for performance, I guess. Like even if you're really concerned about kernel development impacting the performance of your user space application, you could do something like that, or whatever it is you want. This is just sort of a set of tools to make your infrastructure easy to manage in terms of running things on every individual patch. So this is just a set of tools to do that. So yeah, that's all I have. Thanks very much, and any questions?
So Circle CI and Travis CI have a default setting to not build external pull requests from forks because it can be insecure. What processes or plans do you have for people sending malicious things to your mailing list?
Yes, this is an interesting problem. This is something we kind of handle in terms of at the test level, I suppose, and not in the snowpatch automation level. We definitely want to have something. We haven't figured out how exactly this would work yet, but especially for maybe some larger tests that are more involved, having something that's kind of maintainer indicated, I suppose. So for anything that would be big or controversial or difficult to test, it's kind of by default, you don't run that test unless the maintainer looks at it and manually says, okay. So we definitely need some kind of mechanism for that. Ultimately, you're executing code from randoms on the internet. There's a lot you can do in terms of obvious cases, like, you need to manually approve something if it touches a makefile, because a makefile can do whatever the heck it wants. So it kind of just comes down to making sure that the infrastructure you're running this on isn't going to explode if someone's trying to hack it by sending a crappy patch to a mailing list, and also looking at the points of, okay, where do we actually need manual approvals to go ahead and do things? But yes, it's an interesting question and a difficult to solve problem. Fortunately, I've never seen a hostile patch to a mailing list. I've seen plenty of bad ones, but maybe not, maybe not that intentionally. So. Hey.
Well, we've tried some of this stuff before in the graphics area, but how do you deal with the whole baseline? Like, how do you know what all these patches apply to? How do you figure out if that patch requires some other patch set that's gone somewhere else?
There's kind of two things there. The first one is what it's supposed to apply to, and the other one is the dependency issue. So for the dependency issue, we don't have a concrete solution yet in terms of, okay, let's say in the cover letter of a mailing list, someone says, this series depends on X other series that's still on the list, hasn't been merged yet. We haven't figured out how we're going to do that because we really don't want to have any sort of specific metadata to this on a mailing list, or definitely not in a commit log. So we haven't solved that problem yet. In terms of what branch it's supposed to apply to, we have a way to, for some projects that aren't the Linux kernel, indicate, it's alongside, you kind of have like in your email subject, patch, comma, v something, and it's supposed to apply to that branch. That can work in that specific case. Otherwise, we essentially just have a list of branches that could be useful. We'll have like the maintainers next and Linux next and current upstream, and we'll just apply it to all of them. And if it applies, then it was probably supposed to go there. So it's not a perfect answer, but it does seem to work in practice. So that's how we do that. Any other questions?
I have something that needs to be tested on a cluster. At least 2 nodes, even more is better. And can that be done or integrated with what you have done here?
Sorry, could you repeat that? I couldn't quite hear you.
I repeat. I've done something which needs to be tested on a cluster, consisting of at least 2 nodes for runtime testing.
Yeah,
and some storage locally, let's say 100 gigs or so.
Yes. So there's no limitation here. In this case, with our current setup, you could write something to do that on the job runner side. So you could definitely engineer something in Jenkins that could go off and spawn that for you. There's no limitation on our side in terms of what you can test. We'll just kind of start it for you, and then whatever your job or your test runner is goes off and does it. So there wouldn't be any limitation there. Obviously, that'd be a pain in the butt to actually write something that automates, but you could definitely do that. There's been nothing stopping you from doing that or any other particularly complex thing other than your ability to write it. Yeah. Any more? All right, cool. Thank you very much.
Thank you, Russell.